All right, I'm here. So I'm getting questions on how to track the inventory for PA5. Is that interesting to anyone?
Yes.
Okay. So let's run through an example. And let's do a handful of items. So I'll just put in arbitrary numbers here. So there's a fictitious inventory. And let's make a structure. Which has a value associated with it, and then an array of counts. And let's suppose that maxval takes an integer capacity and it returns a struct result. I'm not going to mess with pointers here, I'm just going to return a struct result. So maxval takes the capacity, that's how much your bag can hold, and it returns two things, the value that you can get out of that bag and the collection of how much of each item you need in order to get that value. So there's a few things you need to tweak from the version that's just giving you a maximum value. So something like best val equals 0. And then for each item, if the item fits in the bag, so I'll just use I for our index. So for each item I, if that item fits in the bag, what do we do? We need some temporary result. So if we put item I into our bag, right, take the weight of item I out of your capacity and call maxval. And that will return to you one of these structures that tells you the maximum value you can get out of this reduced capacity, and also will tell you exactly which items and how many of each item to put into your bag to get that maximum value. So this statement right here is being used if we put item I into our bag, right? And we know that we can get a value of whatever the value of item I is plus whatever this max value is. Okay, so we can do something like the following. And let me change our initialization. Let's make our best value a struct. Bless you.
Thank you.
So let's have best be a struct result, and let's set best value equal to 0. So we'll kill two birds with one stone. So best is a struct result. We initialize the value to 0. And now we go through each item, and for each item we say if we put that item in our bag, assuming that it fits, and only if it fits, this is the max value we get out of the reduced capacity. And that value in inventory is stored in temp. Okay, so how do we know if this is a superior solution over other solutions that we've tested? What's our calculation going to look like here? Maybe. What do we want to compare to what?
Compare to the best on the max val of the max of the max val.
So we're just looking at one result here, right? So we're doing a running max.
So when we save it somewhere and find the other option.
So we're going to use this struct best to save our running best. Right, but what's the actual calculation we have to do to know if this putting item I into our bag gave us our best solution so far? We usually just say if temp is bigger than best, then best equals temp, but it's more complex now because we've made max val return a structure. Yeah, this is inherently hard because I'm kind of starting the code and asking you to like jump in and continue writing it. So max val is returning one of these things, right? It's telling us the value we can get out of that capacity, and it's telling us how to get that value. This statement here is saying, suppose we have the value of item I, and we have whatever this result is, temp.value. So if this is bigger than whatever our best value is so far, which is best.value, then we want to do the following. Set best equal to temp, and don't forget to bump up its value. I don't know if this will work or not, but if it makes sense, that's all that matters. Right? So if the value of item I plus the value we get when we fill up the rest of the bag in the best way possible is better than our best value so far, let's take the result of filling up the rest of the bag, save that as our best variable, bump up the value, and we also need to bump up the count of items. Because this solution here is the solution we got from this call to max val with one more of item I. So all you got to do is best.counts bracket I plus plus. That's where you increment the count of that item.
And then max val returns best?
Max val returns a compile. Yeah, so at the end of this call to max val, you mean? Yeah, return best.
Yeah, at the very end.
Yep,
Okay.
you got it. Got questions? Ask him. So it's the same thing as when we're just looking at the max val without worrying about the inventory. We're just doing one extra step basically, but it's scattered throughout the whole loop. The extra step is the value is also paired with the way you get that value. And so when we record the best value, we also have to record the best, the way we got that best value. And when we adjust our best value by setting it equal to max val plus the value of item I, we also need to adjust the way we get that, which is take the way we got this max value, but also add one more of item I. That's what this is doing down here. So don't treat this code as precious. Don't force yourself to try to make this work, right? This is an idea of what we're trying to do, but coded in a way that works for you. The other thing you need to tweak is your dynamic programming. Your save array is no longer an array of integers. It's got to be an array of, in this case, struct results. Because the whole way we're going to use the dynamic programming is, instead of calling maxval, we're going to say, hey, we already called maxval of 5. Let's just copy the value out of an array. Well, since maxval returns a struct result, it's got to be an array of struct results. And when you put things in that array, you've got to make sure you initialize the value to 0 and the counts to 0, so that these increments make sense. So there's housekeeping details to worry about in there also. But that's the basic idea. So questions about that? All right, let's get some exercise. So let's do some work on the board in groups. Let's cut some rods. So I'm going to give you a pricing table for a rod cutting problem. So here's your pricing table. And what I want you to do is go through one pass of our loop inside this maxval. Right, so we're thinking about a maxval function that takes a length of material and is going to tell us what the best way is, what the most value is that we can get by cutting up a rod and selling off the pieces. And so let me do this for one example, and I'll let you do it for another example. So max val of 5. Okay, so I can possibly cut it into one piece, which is worth $4, and then get whatever maximum value I can get out of the remaining 4 inches. I can cut it into a 6-inch piece and get whatever I get out of the remaining inches. A 3-inch piece gets me 14 and leaves me that. A 4-inch piece gets me 16 and leaves me an inch. And a 5-inch piece gets me 21 and leaves me a 0. So we did this yesterday, right? Okay, so I would like you to find a group and find a spot on the board, and let's calculate max val of 4 in the same way. And it's going to be some recursive calls, and I'm going to ask you to work neatly, right? So make one column for max val of 4, another one for max val of 3, another one for max val of 2, another one for max val of 1. Max val of 0 is 0. And then you're going to take that and you're going to plug it in here to find max val of 1. You're going to take that and plug it in everywhere that you have a max val of 1 and work your way back up. So you're going to basically do what your program would do if you wrote code for this. Okay, so but start off with just the outer loop. Well, I mean, repeat this on the board to begin with, and then go down for max val 4 and so on.
Is it a rod of length 10 again?
Is it what?
Is it a rod of length 10?
It's a rod of length 5.
Oh, okay.
Yeah, you can do 10 if you want. All right, make sense? So start working on that. I'll walk around, I'll see what you're doing, and we'll figure this out.
I'm not sure where he does it. I just-
6 from me.
Oh.
Okay. 6. I mean 5.
Minus 2.
6 minus 4. I mean
Nick,
Five.
this start with 4.
4. Well, write down 5 so you can go back and fill it in, but 5 is already up there.
This one, yeah, right over there.
314, 416.
You want to do like
That's just
the result? I think it could be 4 plus max value of 4. Oh yeah. So 6 to 4. No, I think it's 4 plus max value of 4. Like the first one.
Maximum 0 is 0.
I think that's value of 3 times. Yes, so it's value of 4. Oh yeah, I see. This one's 4. I guess slapped on. Yeah, and then gonna be 3.
We'll be able to access it.
Oh my god. Distribution. 6.
Oh, for the value.
14.
Max value of
2.
4. Yeah. 4 plus max value. Basically, is 3.
2 is 6.
It's gonna be 6 or
3 plus 14.
4 plus 4.
The same? What happened? The combination was 4 plus 1. When do we have a max value? Oh, I just write down.
You're working backwards.
Yeah, and so we have like
Takes less work the way you're doing it.
Very hard now.
Oh yeah.
16.
Why do you think we were good?
Yeah, the MX is 3.
Yeah, start from 5 and
Was 4. 21.
I was going to say, yeah, just put M5 you can put all of them over here. You can put 21.
so try to do it in order though. Start from 4.
From here?
Yeah. Do the same thing you just did for 5, but do that for 4.
Okay, so.
And work your way down like that.
So from where?
Oh, wouldn't it be maximum 1 times 5?
Maximum 0 is just 0,
Max value 0 plus max value 1.
So the max value of
Yeah.
is going to be 21, and then that will
That's right, that's right.
that will branch back to
Wait, how did Maxwell 1 end up 21?
We should write the best one.
Oh, that's a 4. Oh, that's a 4? This is 4 and all these. This should be all. Oh.
Yeah, I think you flipped the table.
And you also have.
So yeah, we have 1 and 4, 2 and
See, if you start from that end, you know you're working with max val 5, so you know you're already at 5.
But if you were to go the other
If you were to go the other direction, you gotta do something different.
16 and 2 and 3.
I mean, you make an array of 100 elements and build a linked list of those, so if you need more, you gotta do it at a time. Or you know, you can change the size of the array, but you have to copy everything over. It's hard to expand it in its location. Sometimes that'll work, sometimes not. Yeah, yeah. If you have to copy it over. Yeah.
So how's this looking?
Say what?
How's that looking?
That's looking good.
Why is it better to start from this than?
That's just what the code's gonna do, so we're just kind of trying to explore that view of it.
Do we need to break down these?
Yeah. Yeah.
But does it?
But it's faster if you start from that.
Yeah. So
yeah,
can
yeah.
we just order? We can just order the weight to. So when we order the weight, we just put the largest weight at the top.
Mm-hmm. Yeah, but the way the code's written, it's still going to totally try to find 5 first, which is going to require finding 4, 3, 2, 1, 0, and it's going to start off by, yeah, so if you ordered the weights, it would,
Yeah, it will go here.
Yeah.
And then you'll find 0, and then we can put 0 into that rate.
yeah,
And then we'll go here.
right. And in fact, if you're doing dynamic programming, or once you find your 4, you're going to have found your 3, 2, and 1, so you're never going to have to actually work to calculate those. But we're ignoring that for now. I don't want to see that.
So what's better? Is it better to order the weights, or it doesn't
No,
matter?
it doesn't matter. Yeah.
This one would be, this one would
So now what are you doing?
So yeah, so I mean 5 is the largest of those 3. Right, so figure out what's the largest first, you figure out what so this would be
Seven.
And so here,
What he did was we have value of 5.
so we have found 0, 1, 2. We're gonna find 3 from this case, and then we're gonna find 4. Like into the other, you're gonna be able to put 0, 1,
okay, that was 2 minus 1. It's melting right now.
It's confusing because you feel like you should not be able to support this.
So we're doing
You have to
like,
figure this out first to get that.
are we supposed to find the largest one? I mean, so when we go all the way down to here, we gotta find the, and then we gotta put this into a way, to the way is looking for.
And then
I think so.
It was sitting there
So when
first, but
we
they
get
got
rid
rid
of
of
the
it.
which one largest?
Morning whenever I.
So can you calculate
Which one
MV2
largest?
It was thinking when I got the card.
Largest test, let's find the largest, the largest method.
So then he's gonna start off.
So it's the largest of those 2 expressions.
Oh, the largest? So from the largest from this here and then the largest from all the. Well, are those who find a large arbitrary, then return Yeah, so when we get all the way down to here, we're gonna know that this has not so we're gonna put it into the array. And then we're gonna go to this, and you see it doesn't have like any other thing. Into the array, this is the weight. So we're gonna be able to take one. And so we go to 2. And from, if this one is bigger than that one, we're gonna put that one and we're gonna and then we're gonna go to 3. And there's 3 possibilities with 3. And then when we know which one's bigger, we're gonna put the weight here. And then we're gonna go to 4. And then what possibility to put the and then when we find this one is bigger, we're gonna put it right there. And we're gonna have the weight. So when we start calling these other things like stuff like that, we already gonna have a boundary. So we don't have to do all these spreading. Since in the array we already have the weight.
This one is going to be like how we started. I think I probably understand. Does that make sense?
I didn't realize.
That's why this is nice.
For this whole round.
What do you do to have, because it's either this one or this one?
Yeah, so 22.
We're gonna export.
If you're just looking for the max value, the answer is 22.
Yeah, or like a structure maybe. Like it holds the weight and then the value.
Yeah, that would be interesting. You could do that.
And
Yeah.
so we're gonna go here. And we're gonna support. Every one largest 4. Every 2 largest is either 6 or 8.
Yes, that's what it is. So basically like when we hit
Which is a combination of
3 links.
either for 3 it's gonna be either this one or that one or that one. Combination
This is just whatever your highest value is
which is gonna be
because MB2 highest value is 0. MB1
first of all,
highest value is 4. So you have all of those.
or we have
Making sense? Okay.
and so we're gonna have to have like an if statement that checks the array. So it checks 128, like the 128, and it's for the weight. Yeah.
Yeah, however many you have.
And it's gonna look for the weight and see if it's already in the array.
Is this your save array? Yeah, yeah. So now anytime you want max val 0, 1, 2, or 3, you just read it out of there. Alright. Yeah.
Okay. Location 6 plus location 0. 4 plus location 1.
Good?
You could also decrease that.
Alright, so does this make more sense? Okay.
You have another class today? Let me see
Oh, rainy. Well, that should.
Yeah, it's interesting. So like,
Usually, it doesn't snow during right?
So you're traversing a tree basically, right? Starting with max val 5, you had to calculate max vals of 4, 3, 2, 1, and 0, and do something with those values, add them to the value of the corresponding cut that you made. And to find each of these, you had to calculate a series of max vals and so on. So you're basically analyzing a tree, right? And with dynamic programming, the first time that you do any of these values, they're saved. And so most of the tree ends up getting pruned. All of this does not recurse. Right over here, when we need max val 3, we've already saved it somewhere. So we just read the value from the array and we come back. And we don't go any further down the tree.
So max value is in the root.
Say what?
The max value is the root.
No. Well, when you come back to the root, you'll have found your max value. Well, what you're doing is you're basically saying the value I can get out of 5 is either this, or that. Right? And whichever one is the largest, that's your answer for the max val of 5. And if you know max val of 4 plus, a 1-inch cut, or max val of 3 plus a 2-inch cut, and so on, if you know the cuts that you made to get the max val of 3 and that ended up giving you your best solution, you say, okay, make all those cuts plus throw in a 2-inch piece, and that tells you how to get the 5. And so your solution to how do I get that max value is kind of like a recollection of how you got through this tree. Which particular path did you take that led you to the max value? So I needed a 3-inch piece, which I broke into a 1-inch piece and something else, right? So in some sense, finding the solution that gets you the max val is really sort of looking at how you go through this tree, right? But you don't explicitly make this tree. This is just happening in the recursion. So saving those inventory items and updating the counts and so on is a way to kind of log your passage through this search tree. All right, so we were going to do egg dropping, right? Did anybody think about this or drop some eggs or anything? So we had E eggs and F floors. And we're looking for, value of a problem with E eggs and F floors. We want to know how many experiments do we need to be able to guarantee that we can answer the question, what's the maximum floor you can drop an egg from?
I think can we just start with the maximum amount of eggs?
With what?
Let's say we have 10 eggs, we start from 10th floor. So we can guarantee at least one floor we successfully if it's not going to break from floor 1.
So you start on the 10th floor and...
How many eggs do we start with how many floors?
Yeah, so that's unknown, right? So that's E and F. So if you have 10 floors and you have 10 eggs,
Yeah.
so you're saying start from the top floor?
It's like, no, how many eggs determines how many, what's the starting
Yeah,
floor.
definitely. How many eggs and how many floors? So, and you can try to high-low this, right? So say you have 16 floors and some number of eggs, right? Let's say you have 2 eggs. I mean, you can try to take your first shot at the middle, go to floor 8 and drop an egg. And if it survives, then you've got 2 eggs left, and you know the critical floor is somewhere between 9 and 16. So you've got an easier experiment now. But if you drop from floor 8 and the egg cracks, and you're down to 1 egg, and you know the critical floor is somewhere between 1 and 7. So now you've got to solve a different problem, which is if I have 7 floors and 1 egg, how many experiments do I need?
Wouldn't it be something along the lines of the number of floors divided by the number of eggs you have?
Something along those lines.
Because if you have 1 egg, you have to go through each floor starting from the bottom. If you have 2 eggs, you start from the 2nd floor. And if you have 3, you start from the 3rd floor, and then depending upon where your egg breaks, you just start going down.
But I think we can do better than that. So, without showing you the code, so let's do 20 floors, and let's do 4 eggs. And so it's 5 experiments. If you do 20 floors and 2 eggs, it's only 6 experiments. So it's not a straight fraction. But we can code this up pretty easily by thinking of it as expressing the answer to this question in terms of the answer to other similar but smaller questions. So we have some edge cases. If E equals 1, then we return F. If you've only got 1 egg, you got to start at the first floor, work your way up. And if the critical floor is the top floor, it's going to take you F experiments. Right? If getting to that top floor, you drop it and it still doesn't crack, that's how many experiments it took you. So if your eggs if you only have 1 egg, it's going to take you F number of experiments. If the number of floors equals 1, it's only going to take us 1 experiment. Drop an egg and see if it cracks or not. Otherwise, we got to take an egg and we got to drop it from some floor. So for I equals 1 to F. And let's see what happens depending on which floor we drop it from. So suppose we drop it from the first floor and it survives. We got the same number of eggs, but now we have a building that basically has 1 fewer floors, because we know the critical floor is somewhere between 2 and F. So we have F minus 1 floors, we still have E eggs, and we have to find out how many experiments it takes us. And then add 1 to that number because we did an experiment which was dropping the egg from the first floor. If we drop the egg from the first floor and it cracks, we've done 1 experiment, we have 1 fewer eggs, but now we have to determine how many experiments it takes, knowing that the critical floor is somewhere below floor 1, right? And if there's no floors in the building, we don't have to do any experiments. So in general, if we're on floor I, so drop from floor I, if the egg breaks, now we have to know how many experiments do we need given 1 fewer egg and given 1 fewer floors. If you drop it from the 10th floor and the egg breaks, now we know we have to find the answer to the following question. If I have E minus 1 eggs, how many experiments do I need to find the critical floor between 1 and 9? Make sense so far? Okay, we're going to add 1 to this because we also did an experiment by dropping that egg from floor I. Okay, if the egg survives, we have E eggs, and, sorry, this is I minus 1. They dropped from floor I. If the egg survives, we have E eggs, and we know the critical floor is somewhere between I plus 1 and F. Right, so we have to solve this problem for, is it F minus I or F minus I plus 1 or minus 1? So I equals 7, F equals 10, F minus I plus 1. So if we've got 10 stories in the building, we drop from the 7th floor and it survives, then there's 3 floors we have to test, floors 8, 9, and 10. So it's just F minus I. And again, we have to add 1 because we did an experiment already, which was dropping the egg from floor I. Okay, so these are the heart of our recursive calculation, right? We're going to drop it from floor I. If it breaks, then we're going to have to do this many more experiments to answer our question. If it survives, we're going to have to do this many more experiments, worst case, to answer our question. So this number plus 1 is the total number of experiments to answer our original question, assuming we drop from floor I. And this is the total number of experiments, assuming we drop from floor I, if that first experiment, the egg doesn't crack. So take the max of these, and we can only guarantee the max. Say if the egg breaks, we're going to have to do 3 more experiments, but if it survives, we're going to have to do 10 more experiments. Well, we got to pay attention to that 10, right? Because worst case, it's going to survive, we have to do 10 more experiments. And we're looking for a guarantee. How many experiments do we need? So we find the maximum of this, and we want the minimum of all of these. Because we want to find the floor that will give us the best result, the fewest number of experiments. So we try all the possible floors we can drop from and see how many experiments each floor will require, and then we pick the floor that gives us the minimum number. And that's the value of f of e comma f. So it's a quirky kind of structure, but it's exactly the same concept as what we're doing with rod cutting or with knapsack. Right? It's this repeated substructure, recurring subcases where you evaluate this function in terms of other values of this function. And both of these possibilities, they reduce at least one of these parameters, which means eventually we'll get down to a case where either e is equal to 1 or f is equal to 1, which means we'll pop out of our recursion. And the code is pretty trivial. It takes longer to read in the input and scan it than to do anything else. So to find the number of solutions, we just call the egg function. I did floors and eggs instead of eggs and floors. If eggs is 1, return the number of floors. If floors is less than or equal to 0, return 0. If floors is 1, return 1. Those are your base cases. And if it's saved in the dynamic programming array, we just return that value. Otherwise, here's the 2 cases. If it breaks, we have f minus 1 floors and 1 fewer eggs. So that's this. If it survives, we have floors minus f, and we still have the same number of eggs. Add 1 to those experiments. Pick the largest of those, and if that's better than our best solution, save that. And then just return that as our best solution. Do that over all the floors. So the actual work is a few lines in the middle of a loop. But the recursion is deep. Did we ever talk about Ackermann's function? 224 maybe? There's your ungraded homework. Look up Ackermann's function. It'll take you into a beautiful world. Might be misspelled, but Google knows. All right. We will play around with the Oracle of Bacon tomorrow, and maybe some decision trees and some Huffman coating and some other applications of trees.
One interesting meeting.
All right, I'll see you.